Welcome to this quick session on coastal landscapes and change. So this is looking at the knowledge gaps you've identified in Year 13 in the run-up to your A-level exams. The content of this session is going to be looking at the processes, features and landforms in coasts through use of past exam question diagrams. We're also going to look at isostatic and eustatic sea level change, sediment cells and how they work, and then the two case studies that are major to this topic, a brief overview of coastal recession in Holderness and the stakeholders and players involved, and a brief overview of coastal flooding in Bangladesh in 2004. So we're going to start with this past exam question, and you were given figure 3b on the left, and this is a depositional landscape in North Wales. I always advise when you're given images in an exam, particularly for the 2-6 markers in the coastal section, that you start by annotating the image with what you see, or the satellite map. So on the mark scheme for this image, AO1 identifies the basic general knowledge that exists from this image. So it's identifying transportational and depositional processes. It identifies that there's beaches and we can see there's sand all around the area. There's also spits jutting out of the landscape, as you can see on the west of the map. We also can talk here about the fact that there is salt marshing and mud marsh taking place, and that can stabilise vegetation. Vegetation, of course, is very important to a landscape like this because it stabilises it, it strengthens it, and it protects what's behind it. When you're referring to the map in your answer, please make sure you explicitly do so. So identify any of the features you see in the map, such as salt marshes or sand dunes, so you can accept that that's present here. And then explain how those things are actually created. So the key with this is identifying the features you see, what actually is on the map or the image, and then explaining how they were made. Usually the 6-mark question is about explaining the processes that exist in the image you see, but that then of course leads you to the features that those processes create. So for example, deposition, longshore drift are clearly a process here that takes place, and that is why we have spits, bars and tombolos being created on this coastline. Onshore wind can move the sand backward and create sand dune succession, as we can see in the centre of this map here and going further towards the northeast. Sediment plays a vital role in the deposition here along this coastline, and you can see that there is a constant feed of sediment from the beaches to the north and south of the main estuary area. So the point here is that you've got to identify the names of the processes. So whether it be erosional processes, transportational or depositional, identify the names of the processes, define what they are, say exactly what they are, and how they've contributed to the creation of the landscape, what features you see, and how they have got there. Another example here is of a cliffed coastline. So this is a Caribbean coastal landscape. Now the first thing that should stand out to you is that there are a couple of different layers on this rock. We can see that the very bottom layer of the rock is a wave-cut platform. This whole area is a wave-cut platform, and there is a wave-cut notch being created still in the headland we see there. So you should identify those features straight away. We can see that there are cracks, caves and holes in the geology of this rock, and that is due to the erosional processes taking place. We can clearly see that there are very distinct lines of strata, which are lines of layers in the rock. This rock here, of course, possibly limestone, and therefore we have that layering over time. We then have the top cliffed area of the landscape, and this is suffering from landslides. This is suffering from cliff collapse, and that's as a result of both erosion but also weathering. So freeze-thaw weathering, for example, may exist in some of these areas, but also the lack of vegetation, or vegetation not being strong enough to hold the soil on top of the cliff together. So as you can see, the mark scheme identifies the jointing or the faulting that exists in the rock. It identifies that there are alternative strata or different layers in the cliff. It identifies that weathering and mass movement could take place here very easily. And then it identifies particularly that there are cliffs, notches, mass movement, wave cut platforms, and then it talks through how the wave cut platform has been formed, how the wave cut notch is formed, how subaerial processes like weathering and mass movement take place. And you could also relate this to the tides and how high tide may impact this cliff much more than low tide. And as you can see in this image, it's clearly low tide. We can see all the seaweed deposits left behind, and therefore you can say that it's only some times of the day that we get the action of erosion, whether that be attrition, abrasion, hydraulic action on the cliff and the wave cut platform itself. There's very little evidence of deposition in this photograph, of course, because this is all hard rock. There is no sand. This is general rock that exists. The cliff has existed where the wave cut platform is, but it's receding backward. So again, with this image, you're identifying the general things you see, you're annotating around the image what you see, and then trying to link that to how processes take place and features are formed. The final one I have for you is this one, and this one is a very clear example of a coastal plain or a sandy landscape. And we can see it's quite a flat coastal plain going back into the distance. And what you can actually see is that it is a sandy beach, and you can very clearly see the changes in layers of vegetation as you go back further and further on the sand dunes. So the first thing I would say is identify definitely that coastal sand dune succession is taking place here. We can clearly see that there is levels of change going back in that landscape. So this is a coastal plain, it's a sandy coastline. Transportation and deposition definitely take place on this coastline. It's not an erosional coastline, it is a transport, longshore drift and depositional landscape. Vegetation plays a very important role in that background in stabilising the sand dunes, stabilising the landscape itself, and human actions could have a negative impact on it. But then with the figure 3b itself, go through the idea that there's pioneer species in the Samosyr at the front of the sand dunes. And you can clearly see in the colour and the thickness of the vegetation, the further you go back, the further we move into marram grasses and heather, and then further onwards at the back to shrubbery and so on. And finally, the other thing I'd mention in this photo is the blowout. And that's the area here to the right of the photograph in the centre. This blowout is likely to have been created by human interaction, such as trampling. So human use of the landscape itself is likely to have created that blowhole area on that landscape. So again, this is about identifying changes in the photo, identifying the features that might take place at this landscape, and then trying to explain what they form. So let's move on to another contentious issue that I know a lot of Year 13 struggle with, and it's simply because of the similar terminology that's used and the differing ways you can look at these two things. So we are going to start with isostatic sea level rise or change. The key thing to remember with isosticity and isostatic change is that it is a local change. It does not happen globally, it happens in local areas. And it simply means an increase or decrease in land height, underlined land height. So this is the land changing relative to the sea. It can happen because of plate tectonics, moving upward and downward, or it can happen because there was previous glaciers on the landscape which forced the land downward, compressed it, and when they melt, that decompresses the landscape rises again. For example, the northern upland areas of Scotland in the UK. When the land height increases, so it's decompressed, sea level, of course, falls in relation to the land height. So they do the opposite thing. So if land is higher, sea level falls from that land height and vice versa. So when land goes lower, it's compressed, sea level rises. So the sea itself is not changing in the amount of water that exists. It's the land that is changing in isostatic processes. For eustatic processes, the key thing to remember here is these are global changes. So this is where we actually see global sea level changes. The sea level height changes. This is not to do with land level height. The sea level itself changes. And that happens due to, for example, glacial melt. So glaciers melting on the top of the Alps, for example, can eventually lead to sea level rise, or the Arctic and Antarctica melt can cause sea level rise too. It can also happen because of thermal expansion, the idea that as sea temperatures rise, water needs more space and so it expands. Another reason is because of the amount of sediment on the sea floor. If you have more and more and more sediment on the sea floor, you need more space for the water above it, and therefore sea levels will rise. And it's likely that climate change is actually going to increase the phenomenon of eustatic sea level change. And the reason for that is due to the sea temperature change. As we said earlier, if sea temperatures rise, thermal expansion takes place, the sea needs more space. So the clear difference between eustatic and isostatic processes is there. Isostatic, local land height change. Eustatic, global sea level change. Okay, so sediment cells. You can see a map of the 11 sediment cells of the UK on the right hand side here. And a sediment cell is basically a system. It's a closed loop system. Inputs, processes, outputs. Inputs, transfers, outputs happen in that cell. And there are 11 of them in the UK, as you can see. It's an example of what's called a dynamic equilibrium. It's a balance between the material in the cell being added, inputs, moving, processes or transfers, and removed, outputs. So, what are the examples? For example, cell 1, cell 2. This is Flamborough Head, just at the point of cell 2. That's a transfer point in the Holderness coast, and the sink then is Spurn Head in cell 2. So, all along cell 2 there you can see you've got the examples on the east coast of England. Now, what are inputs? Inputs include cliff erosion, onshore currents, river transport, wind-blown sediment, subaerial processes like mass movement, and marine organisms. Inputs are all things that add sediment to the area. So cliffs erode, the sediment from the cliff goes into that area. We know that the sea and rivers transport sediment to an area. All of these things put in sediment into the cell. Processes or transfers. What moves the sediment? Longshore drift. Of course, upper coastline. Swash and backwash of the sea move sediment in and out. Tidal currents and ocean currents. Tides, of course, day and night, but also the actual movement of the tides and ocean itself. And finally, wind transport of sediment along a sandy coastline. And finally then, examples of sink or output. Examples of where the system gets rid or drops the sediment. Backshore landforms, so sand dunes being created as a result of onshore wind. Foreshore landforms like beaches, they're a deposit of sediment. Nearshore landforms like bars, they're also a deposit. Offshore landforms like barrier islands, they're an offshore deposit. So it's anything that deposits or sinks the material moving. So hopefully that clears up how sediment cells work. Again, just briefly, they are simply a system whereby there are inputs, processes and outputs in a place. And the reason there are 11 different ones along the coast south of the UK mainly is due to the fact that those are the areas where we have sandy coastlines mainly, and those are the areas where we see those inputs, processes and outputs taking place. Now on to Holderness and the Holderness coast as a case study. This is a very difficult case study to go through in a session like this in much detail. So I would strongly suggest you have a look at the knowledge organisers that exist for you, the A-level learning platform, and actually read them. All the information is there for you. But I'm going to round up some of the main ideas here for you. So of course we're talking about the east coast of England. We're talking about sediment cell 2, as we referred to earlier. We're specifically talking about places like Flamborough Head, Bridlington Bay and Spurn Head. They are three key areas of input, process and output. Now the physical factors that affect the Holderness coast are in three main stages. The weather. Storm surges in the winter. Subaerial processes. Waves. Dominant waves with the largest fetch are on the east coast, and that mainly affects the Spurn Head area. And then finally, geology, the rock type. We know that they're chalks and boulder clays. The more resistant chalk has survived. The boulder clays are much less resistant, much easier eroded, and that has resulted in a rapidly eroding coastline. Of course, remember this coastline is one of the most rapidly eroding in the whole of Europe due to its geology. So Flamborough Head is a headland, and it illustrates how erosion can cause cave arch stack and wave cut platforms and stump characteristics. The chalk is resistant, so it is a resistant rock, but it does have weaknesses. There are weaknesses in the strata, and of course wave quarrying or hydraulic pressure creates cracks in that rock, which eventually in turn creates the cave arch stack and stump sequence. But also, as you can see in the image on the left, we also have the idea of a wave cut platform due to the headland retreating over time. Spurn Head is an example of where sediment is deposited because of winds and waves. Now Spurn Head, for example, is a spit that is growing around 10 centimetres a year, and that's because of winter storms. We also have the idea that, remember, we have offshore bars as well, and we have beaches and cliffs and so on along that coastline. But of course the key thing with Spurn Head is it's a great example of whereby you have a spit that is growing, and that's due to the deposits in cell 2 of the sediment cell. And that's all you need to know about Spurn Head. And we're going to move on to the final thing about Holderness Coast that's really important, and they are the defence strategies we see along the Holderness Coast. Now there's a great infographic there on the left hand side for you showing you Hornsey and Mappleton and Withensea and Spurn Head and the differing schemes that have been put in place. It's worth noting that the northern part of the Holderness Coast there's little need to protect, and that's because it is stable, it's less populated, and so there's no real need to actually protect it. However, Hornsey is a holiday resort, so the need to protect that is there, of course, as it's economically valuable. The groins, for example, have been repaired there at a cost of £5.2 million. There have been other things put in place to protect the old seawall that existed there, and the sand dunes are also being protected by planting trees. So the advantages of that are that the groins seem effective, they're low cost, they're acceptable, they're low-lying land, so it is possible to do them. But the disadvantages are that it traps the sand, it can cause terminal groin syndrome, which of course basically means it starves the beach at Mappleton itself as well. At Withensea, we've also seen more management further south. 6.3 million has been spent on beach renourishment and riprap rock and so on. That will hold the line of that coastline. It calms the concerns of residents and hoteliers with seasonal jobs in the area and the risk of losing housing, but it can have limited ability to actually protect the coastline and just holding the line. The costs have limited length of the sea wall, and therefore there is a problem with going back to this area constantly to try and protect it further and hold that line. They're just some of the examples of the defence strategies that have been employed along the Holderness Coast. Please do look more detail yourself at some of the other defence strategies in place. I'd like to move on to how successful it's been in a management strategy as the Holderness Coast. So there is mixed success. Mappleton is a good case study of the costs and benefits. So effectively, Mappleton has had long recorded erosion rates. One village, particularly, 1786 was 35 kilometres from the sea. By 1988, the sea was on its doorstep. So you can see that 35 kilometre change in 200 years. There has been £21 million of EU supported funding for the scheme that was put in place in 1991, which has been quite successful because it has managed to hold the line in the Mappleton area. That included things like rock groins. It also included rock revetment to prevent erosion along that coastline. It also included human management to put in place, for example, car parks, toilets for visitors to improve tourism and the economic value of the area. But more recently in the 2000s, it hasn't been an entire success. The cliffs are showing early signs of slumping again. There is terminal problems in terms of the tourist area where the car park has begun to erode and the roads surrounding it. And therefore we can't say conclusively that it's been a total success, although it has managed to hold the line for a number of years after the 1991 strategy was in place. So hopefully that all provides you with some basic knowledge of the Holderness Coast and how you would use it to look at winners and losers, and how you would use it also to look at the fences actually to put in place. And just on stakeholders and players for Holderness specifically again, I've just done a brief roundup here of the economic and social losses along the Holderness Coast because of management. So the tourist industry, we've had chalets and holiday apartments fall into the sea, so fewer people are visiting. 200 homes will be lost in the next 80 years as the coast continues to retreat. Infrastructure therefore is lost to the sea, and there's no compensation of private property because people struggle to actually get insurance to compensate for it. There have been offers in the East Riding Coastal Change Fund of people relocating from this area and adaptation packages to try and help with the cost of replacing properties and businesses. But these have limited success and they don't actually tackle the problem of erosion themselves. They just try to adapt to those erosional problems. So finally, the three key players that exist along the Holderness Coast are central and local government agencies such as the Environment Agency, the local councils, and funding for all of those have been cut recently, so it's very difficult to actually manage the area itself. We have stakeholders in the local economy such as the tourist industry, farmers, residents who want greater coastal protection because they might be able to get insurance as a result. Insurance companies are increasingly refusing to insure properties in this area due to their vulnerability and what they see as the high risk of the erosional rates in the area. And finally, we have environmental stakeholders such as English Nature and the RSBP, and they want to protect Spurn Head a bit more. They want a continuing flow of sand southward by Longshore Drift because they believe that protects nature, habitats in that area, and also linking back protects the beaches for tourism as well. So finally, on to our last idea of this topic, and that is surrounding Bangladesh as a 2004 and then 7 coastal case study for flooding. Now, the flooding that happened in 2007 of November was mainly due to Cyclone Cedar, and Cyclone Cedar went into Bangladesh from the Bay of Bengal and it brought a storm surge of 6 metres high. Now the reason this relates to coastal landscapes and change as a topic is because of that storm surge idea and the idea that it is a low-lying coastline with a high population. So Cyclone Cedar brought heavy rainfall, strong winds of up to 223 kilometres an hour, and that storm surge. And the coastal areas, therefore, the offshore islands and so on, seen the most deaths and they were the worst affected. Bangladesh is always at risk of flooding, and particularly river and coastal flooding, because it is the world's most densely populated country, particularly along the coast, as you can see on the map on the right hand side. It also has 46% of the population living less than 10 metres above sea level, which is therefore a real risk that nearly half of the population are at risk of a 10-metre storm surge if it were to happen. And there is increasing flood risk as well, and that's due to the subsidence of the landscape, having largely soft rock, and also the removal of vegetation. There has been a 70% drop in mangroves across Bangladesh's coastline. Mangroves, of course, provide protection and shelter against storm winds and floods and tsunamis, and they absorb wave energy, they absorb tidal bursts and storm surges. So if there have been a removal of the vegetation for building and for urbanisation purposes, the risk of flooding along that coastline increases as a result. And finally, as you can see on the map on the right hand side, this is the impact of Cyclone Cedar itself. So the cyclone itself and leading to the flooding. So we can see that in a lot of areas in the south coast, we have over 400,000 people, but up to over 1 million people being affected as a result of the storm surge itself. We had coastal and river embankments breaching, high winds and flood damage, drinking water contaminated as a result, electricity supplies and communications were destroyed as well, and finally it was determined that over 4,000 people were dead or missing as a result of the 2007 event itself. So I hope that overview helps you there with identifying how cyclones can lead to storm surges, and on a coastline like Bangladesh, which is heavily urbanised and populated, but also is very at risk because it is a low-lying landscape, that can then lead to higher risks of flooding. Removing vegetation and subsidence increases that risk, and therefore the problem ensues with coastal recession and with coastal geology along this coastline being soft. Hopefully this whole session was useful for you on the gaps of your knowledge in coastal landscapes and change. Everything else is available to you that you might need to look at, so please do go have a look at it on the A-Level Learning platform. Thank you.